Hello students, myself Shamrat Pal. Today I am going to demonstrate the topic on three-phase full converter with RL load. Okay. What is the benefit for using three-phase full converter rather than three-phase half converter? In case of three-phase half converter, we know the output repeat voltage is 3 Fs, but in this case the output repeat voltage will be 6 Fs. That is why the output voltage and current will be more DC with respect to three-phase half converter. So before going into this topic, we are going through the circuit diagram which is given over here. In this circuit diagram, we are using six switches, that is T1, T2, T3, T4, T5 and T6 as the three-phase converter. That is why input should be the three-phase AC signal. That is why we have given a three-phase supply over here and a highly inductive load is given to the output terminal. As it is the inductive load, that means it will cover the two quadrant operation, first quadrant and the fourth quadrant. Similarly, just like the previous class, first from where we are using the gate pulse, means the selection of the gate pulse. See, that is not from 0, that is from pi by 6. That is why all the cases we mention the gate pulse is given pi by 6 plus alpha, 5 pi by 6 plus alpha or 9 pi by 6 plus alpha. But here we are going to rectify the both half cycle, that is positive half cycle and negative half cycle both. That is why we have used the 6 switches. When T1 starts conducting, then obviously we should fire to the other respective switches, maybe T6 or T2. Similarly for T3, it will next will be fired T4, T2, or for T5 next will be fired, that is T4 and T6. But never can fire the switches, suppose T1, T4, T3, T6, T5, T2. Why? As it will create the short circuit path. Once the path is short circuited, then obviously due to inrush of current, the switches can be damaged permanently. To avoid it, always try to maintain the application of the gate pulse to the switches that never be in the short circuit condition. Okay. Now the operation. As the three-phase signal have given, that is for phase A, there is a signal for phase A, right? And suppose the signal for phase B, which will be the 120 degree apart from the first phase, it will start from 120 degree from the first phase. This is the B phase. And similarly, the phase C, which will start from the again 120 degree from the second phase. So this is the voltage waveform. To make the complete cycle, it will be continued to in this way, as well as the phase B will be complete in this way. Okay. Now see the selection of the firing angle. At the point of pi by 6, this point, okay, we are just taking the close view. At the point of pi by 6 means this particular 0 to pi by 6, all the cases, that is phase A, the value of phase A or the magnitude of the phase A is always less than the magnitude of the phase C. That means what? That means we cannot give the firing angle to the thyristor T1 at this particular position, as all the cases the thyristor T1 remaining in reverse biasing condition. When we can apply the firing pulse to the thyristor T1? When as the thyristor T1 is connected to the phase A, when the phase A will have the maximum magnitude with respect to other two phases, then we can apply the firing angle. Why? See, in the circuit diagram, when the phase A is greater than with respect to other two phases, then thyristor T1 will be in forward biasing condition. Then we can apply the triggering pulse with respect to the other two switches, suppose T2 or T6. But when phase A is less in magnitude with respect to other two phases, then the thyristor T1 will be in reverse biasing condition. If we apply the triggering pulse across the thyristor T1, the T1 will not be fired and the T1 is not be in conducting state. That is why we are explaining this part. So that means 0 to pi by 6, all the cases VAN is less than VCN and VBN always in the reverse biasing condition. That is why we cannot fire thyristor T1. But after crossing the point pi by 6, that means what? Then the VAN is gradually increases with a value. That is why at this particular position, anywhere we can apply the triggering pulse. Here we consider the triggering pulse is 60 degree. That means pi by 6 plus alpha 60 degree, that will give you actually 0 to 90 degree. Exactly. Now go to the operation. See, when, one more thing, the switching pulse, it has maintained the particular switching pulse. Okay, like as we are using the pair of the thyristors, not the single thyristor. As we are not using the pair of the thyristor, though it will not form a closed path, then the current cannot flow to the circuit. Suppose T1 is triggered, no other switches are triggered. That means how the current can flow. That is why obviously when the T1 should be triggered, then the other any switches from the below of your circuit, that will be remaining in the on position. Then the current starts flowing as it created the closed path. Okay, that is why the triggering pulse normally we are applying, suppose a pair, that is T1 T2, suppose T2 T3, suppose T3 T4, suppose T4 T5 and T5 T6, then T6 again T1. As the 6 switches are there, that is why ultimately we will reach the 6. Then the cycle will be repeated in this way. Again T1 T2. That means what? When we are applying the triggering pulse across any switch T1, then the other switch must be in conducting state. Suppose in this particular switching sequence, when we are applying the triggering pulse across the switch T1, then consider T6 was in conducting state. The similar thing we can explain through the circuit diagram and the waveforms. See, in this waveform, when T1 starts conducting or applying the triggering pulse across T1, that means in the previous mode, T6 was in conducting state. That means what? Then the current starts flowing from T1, then load, and coming back to through T6 and to this phase. That means voltage appearing across the load, that will be VAN minus VBN. That means what? That means VAB. Clear? That means the voltage appearing across the switch, that is defined by what type of triggering pulse we are applying to respective switches. If T1 T6 triggered, the voltage will be VAB. If T1 T2 is triggered, then the voltage will be VAC. Right? Correspondingly, we can apply the triggering pulse. Now see, so after crossing pi by 6 to an any angle alpha, we are applying the triggering pulse here for phase A. That means what? When T1 starts conducting, then just I have shown before, then the voltage appearing across the load, that is VAB. That means difference between the two phase voltage, that is VAN minus VBN, right? That means VAN minus VBN. This is the dotted line is mentioned here. That means it will provide output voltage is VAB. This is the input voltage, okay, and this is the output voltage, okay. Now what? After crossing just point this one, means after crossing the point 90 degree or pi by 6 plus 60 or pi by 6 plus alpha, what happened? See, after crossing this, so at this condition T1 and T6 was in conducting state. Which one? T1 and T6 was in conducting state, and the voltage was VAB, and the voltage is VAB, okay. After crossing just the point this one, what happened? See the waveform. Then the voltage gradually increases in the reverse direction, VAC, VCN, and the voltage VBN is gradually increases to the forward direction, okay. In the previous case, means in this particular case, what happened? Think it very carefully, see it very carefully. What happened? VAN is greater than VBN. That is why T1 was in conducting state, forward direction, and T6 was in conducting state in forward direction. But after crossing the point, just this point, what happened? Then VAN is in decreasing in order and VBN is increases, as well as, okay, VCN is increases. That means after crossing the conduction period of T1 T6, the conduction period of T1 T6, then T6 gets reverse biased. Understand? I repeat, just crossing this particular region where T1 and T6 was in conducting state, what happened? In this particular case, VAN greater than VBN, means VAN greater than VBN. Then the both thyristor T1 and T6 was in forward conduction state. As this one is greater than this one, that means current try to flow in this direction. That is why both the switches was in conducting state or forward direction, forward biased. But after crossing this region, I am talking about this region, what happened? Then VAN falls, right? But VBN is increased. That means VBN is increased and VAN is decreased. That means what? Then the switch T6 will be in reverse biasing condition. So immediately that T6 switch will be closed, will be off or commutated. Then we should apply the next triggering pulse across this one or in the reverse biasing this one. So in this way we can continue the total operation. All the forward peaks we are applying the triggering pulse across T1, T3, T5, and for all the negative peaks, suppose this one, this one, this one, we are applying the triggering pulse, that is T2, T4 and T6. So it will be continue the operation. And waveforms. So this is a supply waveform, and we are next we are going to draw another one. First VO or output voltage, which will be taken from the supply voltage, and this is the waveform for supply voltage. Now see, when T1, T6 and T1, T2 conducting. Means when T1 conducting with respect to other two switches through T6 and T1, then what happened? In this particular region, when T6 and T1 was in conducting state, then the voltage appearing across the load is just I have discussed before, that is VAB, because VAN minus VBN. Similarly, in the next case, think about this region and this region. What happened when the thyristor T2 fired in this case? Then the voltage appearing across the load, that is VAN minus VCN, that will give you VAC. Similarly, when T3 triggered in this particular case, then the voltage is appearing across load, that is VBN minus VCN. That means it will give the VBC. Similarly, one more application. Suppose when T3, T4 starts conducting, then the voltage appearing to the load, that is VBN and VAN. That will give you the difference of two phase voltage, that is VAB. That means, see, all the cases it has changed its polarity, right? Similarly, this one, similarly the other two other phases. So in this way, all the cases the output voltage we can form, which is taken from the input voltage. Now the current, output current. So this is the output current, okay, and which has to be taken from the individual thyristor currents. So go to the circuit diagram again. In this circuit diagram, see, when T1 starts conducting with respect to any other two switches, then the current starts flowing in this direction, right? Similarly, when T3 starts conducting with respect to other two switches, then the current starts flowing from B phase to in this direction. Similarly, when T5 starts conducting with respect to other two switches, then the current from phase 3 starts conducting in this way. That means all the cases, the output current from first thyristor T3, T1, or from T3 or from T5. That means the output current which is taken from the three individual switches, which is maintained in the upper part of the circuit, that is by IT1 plus IT3 plus IT5. It will give you the original output current I0. Now, what is the waveform of IT1? Obviously, when the switch T1 is triggered, when the switch T1 starts conducting, then the current across the thyristor T1, that is IT1. Okay, that means first we find out where the thyristor was in conducting state. T1 thyristor was in conducting state. So see, it are reflected on the switching pulse, sequence of switching pulse. See, in this region T1 and T1 was in conducting state. In this region T2 was in conducting state, and in this region T3 was in conducting state. That is why when the T1 is in conducting state with respect to other two switches, so it will be reflected on here. Okay. Similarly, from the T3 means this point T3 and this point. So obviously it will be the output voltage waveform of the T3. Similarly, that will be T5. So after summing these three currents, means this one plus this one plus this one, so which will provide you the exact DC to the output voltage, means the current is completely DC. Okay, so this is a good example for using three-phase full wave rectifier, and this is all about for the phase current IA, IB, IC. Actually, we have got the voltage from output terminal, that is actually line voltage, and similar for the line current. Now we are going to plot the waveform for the phase current, that is IA, IB or IC. So IA means when the T1 starts conducting with any other switches, then IA. So it can be demonstrated with a good example. that is from the voltage waveform. That means the output voltage VAN, this is VAN and VAC. That means what? Then the current starts flowing from phase AN to phase BN or to phase CN. That means it can easily identify the current starts flowing from phase A, this duration. Okay. Similarly, in case of B, that means what? The current starts flowing from B phase to C phase and B phase to A phase. Similarly, the current starts flowing from C phase to A phase or A phase to C phase to B phase. So that is why VAN. So where is the VAN is applicable? That is why VAN applicable, that is VAC is applicable. Again VB, A and VCA. That means what? In this case, we can say current starts flowing suppose from phase A to phase B and C. But in this case, we can say current is entering to the phase A from phase B and phase C. That is why current is opposite in direction. That is why in this particular region, when the current starts flowing from phase A to another phase, that is why positive current. But in this particular operation, when the current starts entering to the phase A from other two phases, that is why the current direction is changed, that is in the reverse direction. Similarly, the other pattern should follow the similar in the similar way. Similar can be applicable for the phase B. So in the first case, phase B means this is phase B, means current starts flowing from C phase to B phase and A phase to B phase. That means current is entering to the B phase, is the opposite direction. Again, then the current again flowing from B to C and B to A means current is flowing from B phase to another phase. That is a forward current is there. And again, the current is negative or reverse direction. Similarly, all the current, the phase current that is directed by these three waveforms. This is the phase current, this is all the line currents, and this is the output current, and this is the output voltage. So in this output voltage, see, now we are going to calculate the average output voltage and RMS output voltage as we are playing with the rectification operation. That is why for calculating the average value, first we should consider where how many peaks are available for a single cycle. So single cycle means 0 to 180 degree, means this point to this point. So if we go through this point, that means what? That means we can say in this particular region, suppose 0, in this particular region, suppose 0 to 360 degree, how many peaks are there? See, 1, 2, 3, 4. Okay, and sorry, is a complete cycle. Sorry, I have it's my mistake. Sorry, we have not selected properly the 0 to 160 degree. That is 0 to 160 degree means, see, is a complete cycle means suppose for phase A it will started from this one to this one. That means this is actually which is 0 to 360 degree. So now we can consider from 0 to 360 degree there is a number of peaks is how much? That is 1, 2, 3, 4, 5 and this half which is called 6. That means number of peaks for a complete cycle, that is 6. Number 1 clue. Next, suppose consider this is the output voltage for application of the firing angle across T1. That this output voltage is confined between the region that is pi by 6 plus alpha to pi by 2 plus alpha. That means in a complete cycle the number of peaks is 6 and it is confined in the region of pi by 6 plus alpha to, that is pi by 2 plus alpha. So that is why it can help us to the further calculation of the average output voltage. Okay, now see, now line to line voltage that I know, that is VAN, which is actually developed inside the three-phase supply, that is VAN is equal to Vm sine omega t, right? VBN is the 120 degree apart from the first phase, that is why Vm sine omega t minus 2 pi by 3, and the phase 3 voltage, that is equal to Vm sine omega t plus 2 pi by 3. It can be written by Vm sine omega t minus 4 pi by 3 also, right? 4 pi by 3 or plus 2 pi by 3, both are actually same thing. Now see, so this is the all about for the phase voltage, but for rectification operation in this circuit, to the output terminal the line voltage is appeared. That is why line voltage means that is the difference between two phase voltage, which I have discussed before in the waveform, that is VAB, that means VAN minus VBN. Similarly, we have done the expression, and we have taken the value from VAN, this one, and VBN from this one and this one. Now we can easily calculate or simplify the terms, that is VAM common part, sine omega t minus sine omega t minus 2 pi by 3. After we are using the formula, that is sine A minus sine B, that means 2 cos A plus B sine A minus B. So similarly, we can achieve the all steps here. See the steps carefully. So ultimately, we have got the line voltage is appearing across the load, that is root 3 Vm sine omega t plus pi by 6. Similarly, we can do the next, that is VBN, that is equal to VAN minus VBN. Put the value of VBN from the first equation and VCN here. After simplification, we will get the result in the similar way. So the voltage, the magnitude of voltage VBC, that will give you root 3 Vm sine omega t minus pi by 2. Okay. Now we are going to calculate VAC. Okay. Now we are going to calculate, that is VCA. So VCA means VCN minus VAN. Similarly, okay. Then do the calculation and simplify form. Then we will ultimately reach, that is the voltage VCA equal to the root 3 Vm sine omega t plus 5 pi by 6. So average output voltage, that is average output voltage means go through the means the picture, the output voltage waveform where the VAB was appeared, and just I have discussed before, it was confined between the two region, that is okay. That means similarly we can write the expression VDC equal to 6 number of peaks, that is 6 by the total confined by the total complete cycle, 6 by 2 pi integration of confine the particular peak, that is we have taken here, that is VAN. That means, and this peak is confined between the region, that is pi by 6 plus alpha to pi by 2 plus alpha. Just I have discussed before. And now next part is very easy. It's a simple calculation. Do the step. I have made the all calculation part here. Okay. And finally, we will get the result of average output voltage for the full converter, that is 3 root 3 by pi Vm cos alpha. Okay. Now we are going to calculate the RMS value. It's a root mean square. It's known by everyone, and I have done the same thing here. That is root mean square. The RMS value means we have taken the same equation, that is 3 Vm square sine square omega t plus pi by 6, or VAB. Okay. That is square term is there, and under root, and remaining as the same number of peaks in a complete cycle 2 pi, 6 by 2 pi, and similarly you can do the all steps I have drawn here, I have mentioned here. So for further simplification, we will get the result of RMS value here. Okay, now do the all steps I have mentioned here, and further it will be described by the final equation, that is root 3 Vm 1 by 2 plus 3 root 3 by 4 pi cos 2 alpha under root. So this is all about for the